Okay, good afternoon, everybody. Happy Friday. So today is our last class. I know, right? What we're going to do is quickly review what we started touching on for SN1, SN2 reactions. We're going to finish the mechanism of SN2. And then we're going to be allowed to compare. So, as you guys remember, let's just go over to our side point. We have SN2, SN1. These are both classes of substitution reactions. They both involve nucleophiles. They both involve electrophiles. They support, or they will change. The nucleophilic group on the electrophile will be bound. You lose the leaving group. This is common language to both of these substitution reactions. The major difference, SN2 goes A plus B. Actually, let's do it in the language we started. Nucleophile plus electrophile in the same step proceeds through a single transition state. SN1, nucleophile and electrophile as drawn as part of the overall reaction. The way that we look at an SN1 is step 1, the electrophile leaving group, we will lose the leaving group to form a carbocation intermediate. In the second step, the electrophile will find the nucleophile to make our product, usually electrophile bound to nucleophile, where there's usually a positive charge and a proton on this. The major thing that makes these two things different, SN2, single transition state, both species are involved. SN1, the leaving group departs first to make a carbocation. Then we get the nucleophilic capture, so the order is different. And it looks like the actual substitution goes to a high energy intermediate, then to our product. That's the sort of substitution part. There's a bit more complexity on the SN1. This product here, the positively charged product, still needs to dump that proton. What we would call this part of the reaction, this is our acid-base step. It's losing that final proton. But the substitution fundamentally are two key steps: leaving group loss, nucleophilic formation. That's why we class this, because in substitution, it's all about those two bond formations. This is energetically what they look like, and because of this, because of different mechanisms, every other consequence, what type of substrates can do one or the other, is defined by this. This is why this is key, because everything else falls into place from here. So we're going to finish off our discussion of SN1 first. Like we said, this is our energetic profile. The substitution part, two transition states. The first formation of our carbocation. The carbocation has to capture our nucleophile. The nucleophile in an SN1 reaction is neutral. It's usually the solvent. It's usually what's floating around. That gives us the product right here. That product is going to be protonated. We have an acid-base step in this last part. This is the loss of a proton from our product after carbocation capture to get us to our neutral product. It's dispensing that final proton. But it's more complex. It's multi-step. In order to make a carbocation, this is the key thing for SN1. The loss of the leaving group, usually with high temperature, all these other things, we form this unstable carbocation. The carbocation, by hybridization, is an sp2 center. This single carbon, being sp2, has the cisplanar geometry. Now, unlike SN1, where we have this sort of pool ball, the backside attack, that sort of inversion, that's what happens to stereocenters. SN1, because it's attacking this flat nucleophile, you have equal probability of the nucleophile coming in from the top or from the bottom. Now, individually, I'm not saying that one molecule both happen. What I'm saying is when you do a reaction, you have a mole of these. You have many, many, many molecules. Every molecule of your electrophile will form a carbocation. Then, from that population, half of those carbocations will be attacked from the top, half will be attacked from the bottom. The whole average of the reaction will be a 50-50 general mixture of these two. You have no selectivity, generally. So you may end up with a mixture of possible products here. So where this comes in is in a step like this. Remember, just like SN2, there's this stereochemical consequence of the reaction. In an SN2 reaction, if the substitution, the reactive center, is not an asymmetric center, often you can't see that that inversion has happened. If the SN2 reaction is happening at an asymmetric center, something where there's stereochemistry involved, that's where you see one center, an R will turn into an S for SN2. Same thing here. SN1 always goes through carbocation. Every carbocation is sp2 hybridized. Where it really jumps out, where there's an immediate problem from this, is if your starting material has an asymmetric center. So here we have, remember, butyl is 4 carbons, propyl is 3, chlorine, that would be my priority number 1. Propyl, 3 carbons, is going to be priority number 2. Oops, sorry. Priority number 2. It's going to be my butyl, excuse me. Propyl is going to be number 3. Methyl is number 4. The lowest priority group is currently facing to the back. We have a single enantiomer, one chiral molecule as a starting material. I have only one stereoisomer of my starting material. This is your prototypical. If you look at these conditions, burn this into your head. This is when you see this. A reactive center that has a leaving group, and it's being reacted with a neutral nucleophile, methanol, not sodium methoxide, not O-, neutral nucleophile. You're also using heat. Again, we'll discuss it in a bit more detail after this, but if you see this pattern, neutral nucleophile with heat, this is typical. These are the recipe for an SN1 setup. High temperature in order to produce these high energy intermediates, neutral nucleophiles as the solvent in order to set up for an SN1 reaction. But in this case, we start with a single stereoisomer, and we end up with 2 possible products. So how this is happening is, remember, the mechanism of this process goes as follows. The first step in my mechanism will be to form butyl, methyl, propyl, positive with the chloride. We lose that leaving group. We form what is an sp2 hybridized intermediate. That's my carbocation. That's step 1. Now this species is floating around in a bath of methanol. Methanol is my nucleophile. So I'm going to draw this MEOH, and I'll specify the lone pairs to show you where that part is coming from. So what we have here is, remember, even though I've drawn a single molecule, this represents every single molecule in the reaction. We're doing this on a mole scale, large scale. There's many millions of these molecules floating around. In that case, these flat molecules, half of them will be attacked where the methanol comes in from the front, half will be attacked, methanol coming in from the back. So when that happens, if we said from the top, I would draw this where, again, if it's a flat molecule, methanol comes in from the top. I'm going to leave my butyl and my propyl in the plane. The methyl will be pushed back, and the O hydrogen methanol, that's my nucleophilic capture, comes out of the page. This will be a wedge. That's from the top approach. Half of the other molecules, this guy, same thing, will attach from the back, the other direction. That's going to get you, again, draw the 2 parts, the butyl, the propyl. As it approaches from the back, think about it where the methyl group is now going to pop forward, and OH methyl, the methanol part of it, the nucleophile, is going to be from the back. This is your substitution. You're going to have a 50-50 mixture of these 2 products that you end up with here. This is not done. Remember, you need to do an acid-base step. Typically, that means that we have to remove this proton. We have to end up at our neutral products here where that final proton has been liberated from the molecule. We just need a base, something to pick that proton off. If these are your reaction conditions, you've been given the starting material, your methanol, your heat. You need something to act as a proton scrubber. So you're looking for something with lone pairs. So what do you have here? You've got methanol, you've got lots of those, many molecules of the solvent. Potentially you've got chloride too, right? Chloride is an anionic center, you could think of that. The usual best accepted reaction mechanism says a second molecule of solvent will do an acid-base step to pick off that product. Or drawn the other way, pick off this product here. This is just probability. You're saying that, look, if I have a positively charged species, it needs to find something with lone pairs to pick it off. If you're dissolved in solvent, 99% of the molecules that this guy's going to bump into is solvent. Probability says methanol is your best proton gatherer. Why might I not pick chloride? What if chloride was to pick it off? Yeah?
Because chloride's fairly stable.
Yeah, chloride's pretty happy. Not saying that methanol loves being positive either, but chloride is pretty stable. What do you form? If chloride picks off a proton, what do you make? Yeah, HCl. What do we know about HCl? Very strong acid. So using him is not the great idea. Also, again, concentration. You're going to be low on chloride. There's only ever going to be as many molecules of chloride as you have starting material. Versus the solvent, there's a lot more solvent around. Probability says solvent wins. Again, there's some flexibility in how this happens. What is important? There must be an acid-base step. You have to lose this proton. What you choose, usually, your solvent's your best bet. Okay? But what's important is this: you have two geometries. Look at these two products. What's the relationship to each other? Are they the same molecule? What is the relationship from left to right? They are what to each other? They're stereoisomers. Are they diastereomers or are they enantiomers? Yeah, one asymmetric center, one goes forward, one goes back. These are enantiomers. Now, SN1 reactions do not always make enantiomers. SN1 reactions at asymmetric centers will make stereoisomers, just like SN2. SN2 reactions, all the weirdness, all the changes of an asymmetric center has to happen at the reactive center. If this molecule were to have another asymmetric center somewhere in the side chain, it may not be part of the reaction. All the business is happening here. So don't simply say that, oh, SN1 reactions makes enantiomers. No, SN1 reactions make stereoisomers. The relationship of your products may be enantiomers or diastereomers. It's just going to mess up the center that the reaction's happening at. So this is what it looks like longhand. Step one, you form your carbocation, right? This is the loss of this group to make these two products. Step two, this is also your rate determining step. This is why, from the kinetic aspect of it, the reaction is controlled by this guy's concentration, the concentration of your electrophile only. Yes?
So if there's only one asymmetric center in the SN1 reaction, does it always return an enantiomer?
Yes, if there's only one asymmetric center, it's being scrambled to both. If your molecule had many asymmetric centers, the SN1 is acting on one of them, the other may be untouched, in which case those would have to be diastereomers. That's right. But the first step, the formation of your carbocation, is rate determining. And again, that goes back to the reaction center. The second step, the addition here, once you've made this very high energy carbocation, solvent just comes in, captures it. Which face it approaches, there's no control. So this is also back to, again, choosing reaction conditions. If I really, really, really had this starting material, let's say I have this starting material, and I started, paid all this money and time to make just this starting material you see here as a single enantiomer. And because I've been contracted, because I need this for my drug, for whatever reason, I only want to make one stereoisomer product. Choosing SN2 is a bad choice, or SN1, excuse me, is a bad choice. Because SN1 must form a carbocation. The carbocation must give you no selectivity. But if you look at your starting material, what's the problem here? Could I use SN2 on this starting material? What is the substitution pattern, primary, secondary, or tertiary, for that reactive center? It's a tertiary, right? There's 3 carbons attaching. Can I do an SN2 on this carbon? No. So this is where you get caught sometimes. Mechanism says SN2 is your choice if you want selectivity. The reaction would not allow that. We must do SN1. I cannot form a carbocation, or I have to form this carbocation. I cannot do SN2 on this. So if I'm making this carbocation, I have to deal with the fact that I will make mixtures of products. This turns into a problem where I have to deal with this part. Mechanistically, it's the only viable path, even if I lose selectivity. Everything about organic chemistry is gain and loss. You have to sort of weigh these balances. So just in general, what you can assume, if you do an SN1 reaction, you will end up with a 50-50 mixture of products. There's some nuance to this, but do not worry about it for now. You will get a 1-to-1 mixture of products. Don't worry about distribution of these two. Okay? So, let's do this one more time. What's the mechanism here? Look at the reaction conditions, the recipe. What does this remember? It's telegraphing something. Starting material, nucleophile, heat. What does this sound like? SN1. The nucleophile is neutral, right? You're using heat, high temperature. What is the substitution pattern of this center right here? Primary, secondary, or tertiary? Yeah, 2 carbons. This is secondary center. Which means this guy, you could, if you wanted to, remember, secondary is in scope of an SN2 reaction. But we've chosen, based on what we've applied, neutral nucleophile, heat. We're forcing it via SN1. Okay, what the mechanism would look like. Remember, step 1, SN1, lose your leaving group. The product I'm going to form will be, and I'm going to draw in the hydrogen to make it really clear. The hydrogen that was left over, the 4th group, not shown in the initial starting material, that is my sp2 center. Over here, this is my ethyl group. There's no change in the stereochemistry here. It's coming along for the ride. Next, I've got this. I got my chloride. I have OH isopropyl. That's this guy. This is isopropanol, IPROH. Right? Remember, that is your isopropyl group. Lone pair is here. It's going to approach either from the bottom or from the top. And again, I'm showing it this way. The arrows are curving differently. That's not as important as remembering there are 2 modes of approach. You could draw and say, this is the motion of the arrows. The lone pair is approaching that carbocation. It's simply enough to say there will be, at this step, 2 products. I will have the molecule. If I was to go by the blue arrows there, my isopropyl group would be from the top, IPR. I still have my proton, I still have my positive charge, but I have not touched this asymmetric center. This is still my ethyl. On the other side of the molecule, wrong color, I'm going to have same cyclopentane group. I approach from the bottom, O isopropyl, hydrogen, and positive, but once again, this center is unchanged. Your ethyl group. We're not done yet. We need an acid-base step. This is where my solvent, isopropanol, will act. Another molecule of this isopropanol is acting as your final deprotonation event. Sorry, that bottom one is definitely terrible. They both are actually terrible. What I was trying to highlight was this. What if I did that? Is that enough? Sorry, let me make it darker. Forward. That's what I mean. From the top, from the bottom. Apologize.
For SN1, wouldn't it ask for the mechanism for SN1 if we have to show all 3 steps?
Yes, if you're asked for the mechanism of any of these, if you are asked for the mechanism of a reaction, you must show every step necessary to get to your products in these discrete sort of pause events, right? Each point, absolutely. Top and bottom, if you're asked to form all of the products, make sure you delineate and say, this molecule here forms these 2 products, one from the top, one from the bottom. The acid-base point, the thing I was trying to point out here, these green arrows, is that enough to describe how the proton right here is lost from this one? Remember, acid-base, how many arrows do you need? For a single acid-base deprotonation, there are 2 arrows. We also must lose this bond. So different molecules of isopropanol will deprotonate these centers. You end up with two possible products, the final ones. We will have our cyclopentane group, where from the top is O isopropyl and ethyl. Second product, from the bottom, O isopropyl, and this is up. Excuse me. Oh, no. Ethyl. So this center, you will have both possible permutations. The other center, the ethyl, we had nothing to do with that center. If you look at these two products, one center has the same geometry at the ethyl center. The other center, O isopropyl, both geometries. These are diastereomers to each other. Both geometries are possible. Okay? What would you call this guy right here? If I'm trying to talk about the relative geometry of the ethyl and the isopropyl, what do I call those? Those are cis, trans. Yeah, ethyl is up, isopropyl is up. You call the ring, the plane, they're on the same side. This is a cis relationship. Ethyl and isopropyl are trans in the other one, opposite sides of your ring. Okay? So, how we can make SN1 or SN2 faster, slower? As we've talked before, the biggest one, the biggest decider that lets us go one way or the other is the electrophile itself, what you're trying to react. Remember, both of these reactions, the kinetic sets, the electrophile matters. The leaving group nucleophile, these are similar, but the biggest one to help you decide is your electrophile. Now remember, SN2, methyl centers were wicked fast. They're easy to attack. Primary centers, still really good for SN2. Secondary centers, still okay. Tertiary centers, SN2, no go. SN1, you have exactly the opposite behavior. Because we're forming a carbocation, in SN2, it's all about getting two molecules close together. Steric interaction is the big key. SN1, you're talking about the stability of the carbocation. Carbocations need help. They need groups around them to help stabilize them. So if you take a methyl group here with just hydrogens around, SN1 is impossible. You cannot make this kind of carbocation unless you're in outer space. A primary one, also not possible. They're way, way, way too unstable. There's only one type of primary system that you might be able to make a carbocation on, would be something like this. If I took this guy and I was to lose that group, the carbocation I make is primary, looking at this center. But why do you think this type of carbocation is kind of okay? What is it about this carbocation that makes it slightly more stable than your normal primary carbocation? Yeah, do you guys see pi sigma charge? Resonance can help you here, but this is the only kind of primary group that's possible. This is the only primary carbon that could potentially do an SN1. For the most part, if you have methyl, no go. If you have primary, no go. Secondary is where there's an overlap between the two. Secondary electrophiles have the best of both worlds. They could do SN1, they could do SN2. Tertiary is your absolute win. Tertiary is your best SN1 guy. So what this means is, just by this category alone, if you take all possible electrophiles, doesn't matter what the leaving group is, if a electrophile is a methyl, it is never going to do SN1, it's only SN2. If the electrophile is primary, 99% of the time, SN2, unless we've got that resonance thing. Secondary, this is where you have a choice. It could be SN2, could be SN1. Tertiary will only ever be SN1. So by just focusing on this categorization, we break the problem down into one sort of squishy part in the middle. It is the secondary electrophiles that the guys have to watch out for. Those are the ones that have this overlap that could do either way. Most of the time, you can categorize it and break it down here. So Of these, who is your winner for SN1? So who off the bat can you eliminate? Who's not even in contention anymore? Give me one of the letters that you're like, nope, there's no way that's doing SN1. So we've got, which one? Which one could you throw out that you're not going to consider for SN1? E. Okay, good choice, right? This is a primary. There's no stabilization near it. This guy's out. This is primary, and there's nothing else helping it out. No way. Okay, what do we have here? This is what? Primary, secondary, or tertiary? So could it do SN1? So this is kind of, yeah, it could do it. Could go both ways. What about this one? Primary, secondary, or tertiary? Okay, we got a tertiary. What about this one? Primary, secondary, or tertiary? Okay, so input. What about this one? Primary, secondary, or tertiary? Okay, so we've now eliminated, of that, while a secondary is possible, we've got 3 tertiary groups to choose from. Let's drop A. So we've got A is out and E is out. Of these 3, give me one feature that you can drop one of these guys out. Why? Give me one guy that you want to take off this list. Yeah.
CL?
You mean in C?
Wait.
Like you mean this guy? Okay, so why are you removing him from your choice?
BR is a better leading group.
Does everybody agree with that? What is a better leaving group, bromide or chloride? Bromide, right? The more, yeah, bromide. What is, remember, better leaving group means what? More polarizable, more stable, right? A good leaving group is something that drops out of this. So yeah, I'm with you. Let's lose C because of your choices, chloride versus bromide. Bromide's going to be a better leaving group. We can now focus on that. Now we're down to 2. We have 2 tertiaries. They're both bromide. Yeah. Well, yeah, so what's the difference between these 2? Yeah, this one here. That one has resonance. Remember, what we're talking about here, so absolutely, D is probably going to be your best bet. What we're doing here as we go through this, if you rank through it, an SN1 reaction, if we do not have the ability to make a carbocation, it is all about how stable that carbocation is. Primaries are dead, secondary are possible. We can knock those out. Number 2, if we can make tertiaries, a better leaving group will always help you. This is fundamental to both SN1 and SN2. Good leaving groups are good things. So yeah, bromide beats chloride. Of the 2 bromides that are both tertiary, down here D has one other added feature. The carbocation you would generate over here. Let me just clear this out. Nope. The carbocation you could generate over here, if I was to lose this group, double bond, we have 1 through 3 carbons. It is going to be a propyl group, and it's a positively charged species. This guy, unlike the others, has pi sigma charge. That positive charge is going to be more stable than the corresponding positive charge of other species. That's going to put this guy over the top. Remember, back to the overall kinetics of this reaction. The rate-limiting step is the formation of this carbocation. Anything we can do to drop the intermediate stability, make it more stable, will help you. So D will be your guide. So, electrophile is your biggest bet. You're looking for tertiary, secondary is okay, resonance stabilization is a big thing. Leaving group, good leaving groups are good leaving groups. Stable anions, this is no different than SN2. So happy anions work. Now there's one other thing that you can add to this feature. This guy here, this is tertiary butyl alcohol. If I was just going to try and do an SN1 reaction on this, what I'm saying is these electrons have to go over here. That means the leaving group here has to be hydroxide, not a very happy anion, right? This is one of our strong bases. But there's an option. I can modify my leaving group. What if I protonate that first? If this is a leaving group, what do you have now? If I do this, what's my product? What do I form if I break that oxygen bond as drawn here? Yeah, this is water. That's not too bad. So what I'm introducing here with this, there's one more thing you have as a handle. If my molecule does not currently contain a good leaving group, or conversely, I want to show you the other one too, if your starting material, your reaction conditions, doesn't have what you're looking for, a really strong nucleophile minus, or a really good leaving group. Remember at the end of the SN1 reaction, we could add an acid-base step. We can lose a proton. You can tag those at the beginning of the reaction too. I can start off with this molecule, and I can force it to do an SN1 reaction. It's not going to happen here. I need to protonate this center first. So what that mechanism would look like would be something like this. For SN1, and this only applies to tertiary groups with, let's say, an OH. I do not currently have a good leaving group, but if I add a really strong acid, I can protonate that. To make this guy. This is where my SN1 pathway will kick off. So leading up, charging your SN1. Normally, SN1 starts with loss of the leaving group. If you don't have a good leaving group yet, use a proton, make your good leaving group. So this allows you to use an acid catalyst to kickstart your process. After that, the mechanism is identical. You lose the water, you make a carbocation, you pick up your nucleophile, your product is here. There's a bunch of reactions like this for you to practice, both in the new problem set we have up. But everything else from this cascade is identical to what we've seen. We just have now added one step in front of this. Where this is similar, and this acid catalysis only applies to SN1. For SN2, we have another pre-step we can do. Remember, let's say we had this guy. It's a primary center. There's no way I'm doing an SN1 on this. But if I really, really, really want, let's say methanol, and I really want to do a substitution reaction between these two, I do not currently have a very good nucleophile, and I have a primary center. But I really want an SN2 reaction to happen. So what we can do is like the other case where we have to get the electrophile ready, this is a case where we need to get the nucleophile ready. If I take a really, really strong base, like let's say nitrogen minus, this nitrogen minus can play over here and do an acid-base step. If I use a base that's strong enough here to yank that proton off, I can convert what used to be a poor nucleophile into a very, very great nucleophile. So all I'm highlighting here is the fundamental substitution reaction is about nucleophile meeting with electrophile. You have SN1, SN2. Based on the substitution pattern, we can select between. It's going to be SN2 or SN1. That's primaries, methyls, those are SN2 category. Tertiaries, those are SN1 category. In SN1, I have the opportunity to supercharge or otherwise kick off my leaving group. I need to use a proton to do that. And it only happens with these alcohol type centers. If I'm using SN2 and I'm not ready yet, a super strong base can be used to yank off that proton to make my negatively charged species. Yes?
So why is polarizability prioritized over electronegativity when you're just talking about the leaving group?
Sorry, say that one more time.
Why is polarizability prioritized over electronegativity?
So in this case, if you're looking at chloride leaving versus bromide leaving, stability of your anion wins. So if I have my two choices, I have a nucleophile, let's say it's ethoxide minus. So here, let me give you an example. No, let me go here. Let's say I have iodide versus chloride, and I have MEO minus. In this example, what is your nucleophile 100% of the time? MEO minus. This is my nucleophile, right? Now what I have is I have a mixture. That's going to be a nucleophile. These are my two possible electrophiles. And I'm asking the question, who's going to win? The competition I'm doing here is this guy's going to attack to lose iodide versus that guy's going to attack to lose chloride, right? Everybody with me? This is my choice. Oxygen is always going to attack. The question is iodide happier to lose or chloride happy to lose? Of those two, what would you rank? Who's a more stable anion of the ones you're forming here? Iodide or chloride? Why? It's more polarizable. That's what I mean. We're not competing, oh, strong base versus polarizable. You have iodide and chloride, and the question you're asking is, which of those two is more likely to stay as an anion when we're done? Iodide is a more stable anion versus chloride. The more stable anion is the one that's going to end up on that side of the products. Make sense? Okay. So, the point here, we have SN1, we have SN2. The final complexity here, we have the ability to either supercharge the leaving group with a proton, that's SN1. We have the ability to supercharge the nucleophile with a strong base, that's SN2. Those are one example I can do up in front. The last thing for SN1, the nucleophile is the solvent. Unlike, if you're dealing with SN2, we have this beautiful way of adding just the nucleophile we want. It can be sodium ethoxide, it can be lithium cyanide, right? It's one of those salts, those negatively charged species with some kind of salt from the left-hand side of the table. SN1, you are dramatically more limited. It has to be a neutral nucleophile. It's going to be your solvent. So because of that, if you see neutral nucleophile and heat, you're talking SN2, or SN1, excuse me. If you see a negatively charged nucleophile, strong bases added to the system, that's going to be SN1. Ah, SN2, my gosh. This has been a long term, guys.
Almost over.
So these, are, again, are head-to-head. Let me just give you this in graphical form. I always look at it like this. If we do SN2 on this side, SN1, what we're saying is SN2 kinetics, rate, is equal to K, nucleophile, and electrophile. Over here, SN1, rate is equal to K times electrophile only. The kinetics are different because the mechanism is different. 4 asymmetric centers. Let's say this is 1, 2, 3, and 4. In this case, you will get inversion. 1 stereocenter makes 1 stereocenter product. You have control. In the case of SN1, you end up with both geometries, 1, 2, 3, 4, as well as 1, 2, 4, 3. You get scrambling. The rates are different. Why are the rates different? The mechanism is different. The mechanism being different leads to this consequence. Inversion only in SN2, scrambling in SN1. As far as how you decide between these two, SN2 is all about reactive center here is going to be your methyls. And your primaries. So these are methyl substituted or primary substituted centers. Those are the real dominion of SN2. SN1, what you're looking for, are tertiary. This is your biggest way to separate between these two. Secondaries are the only overlap. If we have a secondary, that's where we need to move to some of these other parameters. Goodness of the leaving group. Are you using heat? These other steps to separate between the two. This is our sort of our head-to-head difference between them. Okay? So, like we said, these are the characteristics which are common for each of these different reactions. Electrophiles, the biggest thing you have to do, this is your substitution pattern, and this is what you invoke first in order to separate one versus the other. So a guy like this, could this do SN1 or SN2? First of all, where is your reactive site? Where's the carbon that has a leaving group attached to it? What's your leaving group? Bromine. This is my leaving group. That's my reactive center. Could this do SN1? Why? Secondary, but what's next door to you? Double bond. Will this have stabilization? So this could do SN1 because the carbocation I would generate is not too unstable. Could it do SN2? Is it too bulky? No, we're in that secondary. This is both secondary and resonance. This is SN, not 2. Oh, man. This could do SN2 or SN1. These are the hardest ones to deal with. But if you look through these different systems, everything on this side, these are SN2. Everything over here is SN1. It's this squishy part here that you target. If you can identify where the reactive center is, this will be your biggest cut that actually allows you to decide which side of that you're on. So no matter how complex the molecule looks like, focus on this part first. This will help you get out of the weeds. Second thing, too, is your rate. Remember, SN1 reactions, it only depends on the electrophile concentration. SN2, the nucleophile. What this just means is, if I had a secondary center and I was trying to guide it only to SN2, I could crank up the concentration of my nucleophile. I can increase the rate of this reaction because the nucleophile appears here mathematically, it doesn't in the first. If I were to increase the concentration of my nucleophile, I can favor SN2. Now remember, what is typically your nucleophile for SN1? For an SN1 reaction, your nucleophile, is it negative? SN2 is negative. SN1, your nucleophile is typically what? It's neutral, and it usually is what? It's usually your solvent. How do I increase the concentration of a solvent? Well, okay, I'll add more solvent. Yay. It's solvent. There's almost no way to increase your nucleophile concentration. If it is your neutral solvent, you're as good as you're ever going to get. If I'm adding something to the reaction, like sodium cyanide, sodium ethoxide, I can crank up that concentration. I can push this thing to SN2. So that's where looking at the reaction and focusing is good. The number of organic products in terms of what happened, if you're doing the post-op. If I do a reaction and I make only one stereoisomer product, that means I must have gone via SN2. If I do a reaction and I end up with multiple stereoisomers, it must have been SN1. So you can use the distribution of your products as a forensic test for what mechanism must have happened. Yes?
Wait, okay. So you said increase the concentration of the nucleophile and
Yes.
that will make it SN2?
2. Yes.
Okay.
Because
But then you said you also can't really increase the concentration for SN1.
what I'm saying is the nucleophile is irrelevant for SN1, partly because it's the solvent, partly because it doesn't even show up in the rate equation.
Oh, so you mean if it changes the rate to increase the concentration?
Exactly.
Okay, I thought
Yeah.
you meant that you can switch
No.
the reaction from SN1 to SN2 by like...
No, what the best you could do, if I had a secondary center and I was trying to push it to SN2, dump in more nucleophile.
Okay.
If I am dealing with an SN1, and I'd be like, oh, I'll increase the nucleophile. Well, the nucleophile is a solvent. I don't even have that as an option. I can't help myself there. That's what I mean. Sorry. That's also this point here. Which nucleophile you use, SN2, neutral, solvent. You have very, very, very few degrees of freedom. SN2, your nucleophile is your anionic species. Look for, remember, what were the typical choices that we used? The best cases we had here were things like potassium, cyanide, or lithium hydroxide, or let's say sodium and methyl. Every SN2 nucleophile is going to look something like one of these salts. It is a negatively charged heteroatom, like an oxygen, like a carbon, like a nitrogen, a sulfur, with some type of other salt, calcium, lithium, potassium. Anytime you see one of these species, we chose that for a reason. We put this in here because we're trying to favor an SN2 reaction, not SN1. Okay? The last part to this too is what we call protic solvents. Do you know what the word protic means? Proton, right? A protic solvent is something like HOH, or something like MEOH, or let's say ethyl sulfur H. To be a protic solvent means you have a neutral charged species with a heteroatom and a hydrogen, right? That's also the definition we use for neutral nucleophiles for SN1. If you have a system like this, if your solvent has an OH, an SH, an NH, you're setting yourself up for SN1. A solvent in that case is your neutral nucleophile. You have a heteroatom, which has lone pairs. This is your guy you're really focusing on. Aprotic solvents. So these are my protic. Aprotic solvents would look like stuff like this. Or molecules that look like this have polar charges. But look at this guy here, this ring. Do anybody know what that is? Well, what type of functional group is this top guy here? If you had to see, an oxygen in the middle, carbons on both sides, we call that it is an ether, right? Proton, like systems like this, where you have heteroatoms, but there's no hydrogens attaching to them, these are aprotic. Having a solvent like this, something that's aprotic, that is typically what we use for an SN2 reaction. Guys on this side, protic solvents. These are SN1. These are all our SN2. Okay? And again, the reason why. Guys like this, these are our neutral nucleophiles with these hydrogens. These will be the ones that we end up using. So,
here's what I found.
Thanks. Oh, and even pulled up hydrogen. How about that? So here's your favorite polar protic solvents. Every one of these has an OH, NH, C, like not carbon hydrogen. You're looking for heteroatom type ones. All of these, if you run the reaction in this solvent, it's an SN1. Aprotic solvents, guys like this. You have heteroatoms, but notice, CH is okay. Your nitrogen, your oxygen, every one of these heteroatoms, there's no hydrogen attached to them. These are your SN2 favored. This is your last scraping the bottom of the barrel. We go to something like this if we're really, really, really trying to push. But look at this one. SN1, SN2, or both. What is your nucleate, or what is your substituted group? Primary, secondary, or tertiary? This is? Primary. So it has to be? SN2. That's right. What about this guy? Primary, secondary, or tertiary? Primary. So it has to be? SN1. Perfect. Last one. This is? This is both. So if you get a guy like this, that's where you have to look at it and say, am I doing it with heat? Do I doing it in the solvent? Is there no nucleophile given? I would push it to SN1. If I'm doing it with sodium ethoxide, with a negatively charged species, if I'm doing an aprotic solvent at low temperature, that's SN2. That is it, guys. Welcome to the end. So, one more final announcement. Next week, I have office hours on Monday. Normal class time, I will be in the S block. I have time available if you have other questions and stuff. I'm happy to set up a meeting. Other than that, it's been an absolute pleasure. I will see you guys soon. And I just realized, this is my last Chem 123 at UBC too, so. No. Well, I've been doing this class now for 7 years, it feels like. Because of that, I have a sabbatical next year to set up a bunch of things. When I come back, I probably will not be in charge of the course anymore. They're going to rotate me somewhere else. So I'll see you guys in upper years. After that, I'll see you guys later.